So now that we know the data path of the TX-0, let's next look at the control and the instruction set. And for that, it will be useful to refer to the flow diagram from the documentation. We can see that the TX-0 is organized as a series of time pulses TP1 to TP8 arranged in a circular fashion. And one chain of TP1 to TP8 is called a cycle. These time pulses are generated by a clock that cannot be stopped, so the TX-0 is always doing something. This is in contrast to other machines that could stop the clock completely. And we see that in this flow diagram there are three distinct paths that the machine control can take. The left one here is the standby path, which indicates that the machine is not really doing anything and just waiting to be started or restarted. And in the right path we actually have two, and these are the machine executing something. The left branch here is the cycle 0, and the right half here is cycle 1. In cycle 0, the machine is reading an instruction from memory mostly, and in cycle 1 that instruction is executed. So each cycle also corresponds to one complete memory cycle, meaning read and write. Now with that in mind, we can understand the instruction set of the TX-0. As I mentioned, the TX-0 was modified a number of times during its lifetime, and in this series of diagrams I tried to show that evolution. Now unfortunately, since I chose a common format for all of these, it's not a perfect match for the original configuration from 1956, so you'll have to excuse that. It says 1958 here, but the only real difference between 1956 and 58 is that the original 64K memory was removed because it was to be used on the TX2 and replaced with the smaller 4K memory, which was later expanded to 8K. So let's take a look at the tables. The TX-0 has four main instructions encoded in the upper two bits of the instruction word, bits 0 and 1. Bits 2 to 4 are not used for instruction decoding in the original configuration. These are only for the later modifications. So 0, 0 encodes a store instruction, which places the accumulator into memory at the addressed location. 0, 1 adds the word at the addressed location to the accumulator, and 1, 0 encodes the transfer of negative instruction, which jumps to the addressed location if the accumulator is negative. So there is no way to jump if the accumulator is positive. And finally 1, 1 encodes the operate instruction, which does not use an address, and instead the bits are decoded in a different way, which is shown in this right and lower table. So the way this works is that individual bits or bit combinations indicate that specific operations, the ones that we've seen in the discussion of the data path, are to happen at different points of time during a cycle. So the upper table here is for cycle 0 and the lower table is for cycle 1. The number on the left indicates at which time pulse these operations happen. So let's look at an example. If we set bit 2 in an operate instruction, that will clear the left half of the accumulator at time pulse 8 of cycle 0. If instead we set bit 3 that will clear the right half of the accumulator. If instead we set bit 12, that will complement the accumulator. So if now we combine these 3 bits in a single instruction, we see that at time pulse 8 cycle 0, the full accumulator is cleared to zeros, and then at TP2 it is complemented, giving all ones, or -0 in one's complement. So you can see that this is quite useful, because if you do it before a transfer of negative, that gives you an unconditional transfer, because the accumulator is guaranteed to be negative. Also, if you do it before an add, that will give you a load, because 0 plus anything from memory is just that value in the accumulator. And you can combine these things in various interesting ways, and it's quite surprising how many possibilities there are to form useful instructions. So, as another example, we can do the AMB operation, which moves the accumulator to the memory buffer, and then move the memory buffer to the live register, and together this of course moves the accumulator into the live register. And if maybe we want to have the accumulator cleared afterwards, we can just set the partial add bit, which does an XOR between MB and the accumulator. But because MB is still is the same value as the accumulator, the result will be 0 in the accumulator, +0. So this is quite interesting and quite rich. And it was modified and expanded to some degree in the later incarnations, as you can see. Yeah, so let's next look into the I/O group. This table suggests that bits 4 to 8 are somehow decoded together, but at this point in time, in 1956 or 8 even, that is not actually the case. 4 and 5 together are decoded, and 6, 7, 8 together are decoded. But as you can see in later incarnations, they really do form a grid, so this is just an artifact of the presentation I've chosen. So for bits 4 and 5, we really have only 2 possibilities, 1, 0 and 1, 1, and these encode the I/O stop and the halt operations. Both will halt the machine, but the I/O stop will put it in a state that it can be woken up again by the completion of an I/O operation. So this I/O stop operation should always be combined with one of the actual I/O operations, so the machine can wait for I/O to finish. So for I/O we have these 6 operations. 2 of them concern the paper tape reader. One of them reads 1 line of paper tape into the accumulator, and since 1 line is 6 bits, if you read 3 lines, which is done by the other instruction, you get 18 bits. So that's a full word in the accumulator after this I/O operation. Next we have the paper tape punch, and these operations will punch 6 bits of the accumulator on paper tape. And you can choose whether you also want to punch the 7th hole or not, depending on the instruction. Then we have the print instruction, which prints a character encoded in the accumulator on the flexowriter. And lastly, we have the display instruction, which displays a point on the scope. The X and Y coordinates being the left and right half in the accumulator. So this is probably the reason that these can be cleared separately as well. So to conclude this discussion of the TX-0 instruction set, and before we jump back into the logisim, I just want to give a quick overview over how the machine changed over the years. So this is how the machine looked in 1960. First of all, the memory was expanded to 8K, and they added a few instructions. The first instruction was the unconditional transfer, which is of course quite useful because not being able to jump while the accumulator is positive is quite limiting. Secondly, it had store and load instructions for the live register, so it no longer had to go through the accumulator. And they also added a bitwise OR and AND to the operate instruction. By June 1961, the main instructions hadn't changed, but the operate instruction was reorganized a bit. So first of all, CLL and CLR had now been moved into the I/O group to make space for more bits for more useful or more often used operations. Also, the timing had changed a bit. So A and B is now done in at time pulse 7 in cycle 0 instead of time pulse 2 in cycle 1, and so on. So this all changed slightly. And then the big change came, I think, not too long after June 1961, but it was certainly the state of the machine by 1965. And at that point, they most importantly added an index register. So this improved the addressing capabilities of the machine. So instead of using only direct addressing, you could now add something to the index register and use that as an address for the instruction. And as a consequence of that, they added a lot of instructions that use indexed addressing instead, so STX and ADX, for instance, being the indexed version of store and add. And the operate group, of course, got more operations that had to do with the index register. And of course, already by 61, they had added more I/O instructions. So this is sort of the final state of the machine, but as I said, I'm not going to talk much about it, just to give you an impression. So now let's look into the control of the machine. First of all, we have the time pulse generator, and it generates the 8 time pulses that we have seen. When I start the clock, you can see the 8 wires lighting up in sequence. And I can also do this manually from this push button here. Now this is not original, this is just my simulation. Next we have the start-stop logic, which decides whether the machine is to halt or set running. And as we have seen, the start-stop flip-flop SS indicates that state, the standby versus run state. But we only want to change this SS flip-flop at the end of a complete cycle, so at TP8. And to synchronize the start and stop conditions from the I/O devices and the push buttons, we have two synchronized flip-flops, the I/O synchronized flip-flop and the push button stop flip-flop. And if any of these is a 0, that indicates that the machine is to halt, and if both of them are 1, that means the machine should be set running. And finally we have the cycle and mode logic, and we've already seen cycle 0 and cycle 1, the fetch and execute cycle of the machine. and this is the C flip-flop that you can see here, but I have not said anything about the machine's mode yet. So there are three modes: normal mode, test mode, and read mode. In normal mode, the machine is executing instructions from memory sequentially, just like you would expect. And in test mode, the machine instead executes instructions from the switches. The instruction coming from the memory buffer test switches, and the accumulator contents are taken from the accumulator test switches. And this is used for examining and depositing memory and starting the machine at an arbitrary address. And next we have the read-in mode, in which the machine is executing words from paper tape, and this is used to load a program into memory from paper tape. So the control signals that we have here are set C0 and set C1 to control what cycle to go into next, set normal to jump from test or read-in mode into normal mode. We have halt and IO stop into the start-stop logic. And from the push buttons, we have the test and read-in buttons, which start the machine in test and read-in mode respectively, and these also go into the cycle mode and start-stop logic. And we have the stop push button, which just halts the machine, and restart, which restarts the machine from the state that it last was in. There are also a few switches that can be toggled, so I'm not going to go into most of them, and I haven't even figured out what the auto, restart, read-in, and test switches even do. But the stop C0 and C1 switches are quite useful, because with those you can single step the machine by cycles. Not by full instructions, but by cycles. Now, to finish off this video, we'll just take a quick peek into the control elements here before loading and executing an actual program in the next video. So let's go in here, and you can see, let me zoom out, that this is quite a bit of logic going on here. But it's essentially a transcription of the flow diagram that you've seen. So let's just take a look at maybe one or two signals here. So, for instance, the AC to MBR signal always happens at TP2, and we have three conditions under which it can happen. The first one is this one here. So the machine has to be in run state in cycle 0, and it has to be in read-in mode. Read-in mode is a sub-mode of test mode, so both these flip-flops have to be 1. So when these four conditions are true, then AC is transferred to MBR. The next condition is that the machine again is in run state, but this time we're in cycle 1, and now there are two possibilities again. Either this is a store instruction, so if we want to store AC in memory, we have to first transfer to MBR, so this makes sense. But there is also the operate instruction, which has a combination for moving AC into MBR, and that's bit 17 is 1 and bit 16 is 0. So if any of these three conditions are true, then AC is transferred to MBR at TP2. And all the other signals are very similar in this way. So let's maybe look at a control signal like set normal. So this will set the machine into normal mode, and it happens at TP8, which makes sense because it's at the end of the cycle that you decide what mode or cycle to go into next. And again, the machine is in run mode and it's in cycle 0, and the instruction is a transfer instruction. So whenever you're in read-in mode or test mode, a transfer instruction will start the machine it will make the machine go into normal mode and start normal execution. And you can just go through all of these and check that they correspond to the flow diagram. It's not quite complete, of course, because I don't have the I/O devices, but otherwise it should match the flow diagram. So now we can check the cycle mode, cycle and mode element. It's not so interesting, just setting flip-flops and clearing flip-flops. Let's take a look at the start and stop logic. Now this is a bit more interesting. We have these signals mostly setting the synchronization flip-flops, and then at TP8 we have certain conditions under which to either clear or set the actual SS flip-flop. Now the time pulse I did not do accurately. I just used a logisim decoder here, but this would probably have been done with 3 flip-flops arranged in a counter so that at each clock tick it would count from 0 to 7, and then you could decode this counter and gate the clock tick with the output of the decoder. But I just did it like this here. And this is the push button logic, which just is very simple too. In the next video we'll be executing a simple test program by stepping through these individual pulses and observing the control signals that come out of the control block here. And we'll also run a more interesting example program just by letting the clock tick. So I hope you enjoyed, and thanks for watching.